Okay, hi everyone. My name is Aryan. I'm 17 years old, and today I'll be talking a little bit about machine learning. So let me just share my screen. So, yeah, let's start. So before I start, I want you to do like a simple little test. Um, Actually, no. These are the types of machine learnings, right? There's multiple types of machine learnings. These are the six main ones. There are other ones, but they're kind of under development, so we won't be talking about those. Artificial neural networks. So this is the main one, and this is what we'll be going over in depth today. So yeah, this is the exercise I was talking about. Before I start, I just want you to see these three pictures, right? They're three Matryoshka dolls. They're pretty common in Russia, right? And I just want you to see them for like 2 seconds. And now I'm going to show you another picture, and I want you to identify if that's a Matryoshka doll, okay? So is this a Matryoshka doll? Obviously, it is. Like, it has resemblance to the first three, so it is. But that's what's intriguing to me, because as humans, we never saw the next picture. We only saw these three pictures. We've never seen the fourth picture in our lives, but only based off of these three, we were able to tell that this is a Matryoshka doll. So the same way we can program machines to learn that as well. So I'll quickly run over how humans learn. So we'll take the same identifying objects analogy. So say, for example, you saw the novel object, then you see other pictures of different angles of that same object, right? So your brain constantly takes this information and then kind of creates that, okay, whatever looks like this is a Matryoshka doll. Then even though you've never seen this, you've never touched this, the fourth picture, without any reference, you could tell that this is a Matryoshka doll because your brain, based off of three pictures, learned how it looks. So the same way we can do that for machines. So there's two main steps. There's called training and then testing. We call the process of continually looking at different views and angles of the picture the training stage, where we're training our mind continuously how to identify the toy. And then the fourth picture was the testing stage, where we check if our mind learned correctly if how to identify Matryoshka dolls. So the same way we can train a computer or AI on some data and then test its accuracy on a new piece of data that it's never seen before, right? So I want to give you a small example. Let's say there's a boy named Timmy, okay? And Timmy can like a toy or can dislike a toy. He can love a toy or hate a toy based on either how complex the toy is, like it has lots of motors, lots of moving parts, and the size of the toy. So in this case, there's two inputs. We give the toy complexity and then the toy size. And then the output is, does Timmy like the toy? Yes or no? So first, what we need to do is we need to get some training data. So here we have, I made a little graph for you. So the red ones are the toys that Timmy doesn't like. And then the green ones are the toys Timmy does like. So as you can see, if it's very small size, Timmy doesn't like them. Or if the complexity isn't a lot, Timmy doesn't like them. Then the computer, based on this data, can generate a line of best fit. So when I gave this to my program, this is the line it came up with. So the basically what this means is the program saying everything on the top right of the line is a toy that Timmy likes, and everything on the bottom is a toy that Timmy doesn't like, right? So now we can have a toy, for example, that one, the little spot there, which can be this size and this complexity. All right. And this is a toy Timmy's never seen before, the AI hasn't seen before. So we can plot that point like so. And because the point is on the top right of the, sorry, the point is on top right of the line, we can be confident in the prediction that it's going to be a yes. Now, how do we come up with the confidence score? So basically the confidence score is the distance between the point and the line. So the longer the distance between the point and the line, the more confident the AI is going to be. So right now, as you can see, it's pretty close. So the AI is only 65% sure Timmy will like it. And yeah, it was correct. So Timmy did like it. So what we did was we got some training data. We created a line of best fit, deciding where Timmy likes the toy and where Timmy doesn't like the toy. And then we tested the data based on a toy Timmy's never seen before. Now, if I wanted to do this with traditional machines, I would have to have every single toy in the world plotted on this graph. I could not have only 20 or 30 toys because when I introduce a new object, the machine's never seen the object before, so it doesn't know if Timmy will like it or not. Now, that is obviously very unrealistic. I cannot buy every single toy for Timmy. So this is where machine learning base essentially comes in, where we can give it some data and then the machine can teach itself how to classify whether Timmy likes it or doesn't like it. In traditional machines, what you would do is you would have every single toy in the world plotted on a graph. And then one of those toys, if you enter, the machine will search it in this huge data set with a lot of time and then tell you if it likes it or doesn't like it, right? 1 second. So, for example, another use case could be recognizing emojis. So, for example, walking, running, cycling, surfing, dancing, horse riding, gymnastics. These are a few activities. Now, what the traditional approach would be, for example, if I wanted to know what cycling is, I would ask is the picture using legs? If it's true, then is the leg length 0.75 meters? If it's true, is the head straight? If it's false, if are shoes two, is he wearing two shoes? Then arm length, then back straight, and then I would find out if he's cycling. And all these parameters I would have to calculate manually by measuring the picture over and over again in this case, right? So as you can probably see, that is not very efficient. The code is extremely long and messy. If there is one error, it will be very hard to find where the error is because there's so many lines of code. And this is only for one activity. Imagine for like 100 activities, how long the code would be. And if I wanted to update this, for example, instead of just these 7 activities, I wanted to add an 8th one, it would be extremely tedious because I would have to add an if statement for every single thing. And then because it's using so many lines and so many variables, it is very, it takes a lot of memory, essentially. It's very heavy for the computer to run. So what can we do instead? Well, we can use the machine learning approach, where I give it 6 emojis and tell the machine beforehand that this is cycling. Okay, so the machine doesn't have to figure it out. I will tell the machine that it is cycling. And then the machine will teach itself whenever the machine will teach itself how to identify the cyclers. So essentially, when I run this code, when I ran it on my computer, the machine outputted that if the image contains a helmet and a bicycle, the activity is cycling. And that is so much more simple than having so many if statements. That is just extremely redundant and repeating. So what we can do instead of that is we can just tell the machine that here are 6 images of cycling, and this is activity cycling. Now I want you to figure out why it's cycling. And the machine can continually use those 6 images and teach itself. So when I give the machine a new object, for example, this one, the machine's never seen it before. But as soon as it realizes there's a helmet and bike, it can correlate that those helmets and bikes are the same. And that is why this is equal to cycling. And as you can see, the machine is obviously correct. So this is the machine learning approach towards things, rather than using the old traditional approach where I have to calculate every single variable and I have to teach the machine. This one, the machine can just teach itself, right? So there's essentially more or less 5 steps. Obviously, this can change depending on your use case, but usually we take it as 5 steps where we collect data. So in this case, the data was the cyclers, the 6 pictures, all right? Then we prepare the data, so we get rid of any unnecessary data like the background or anything like that. Then we train the model, and this usually takes 1 or 2 hours. Just feed in the pictures and then let the computer do the teaching training, Then we evaluate the model. Evaluation basically means, like in this case, when I gave another emoji, the 7th emoji, that's how I evaluated if it's correct. If it says it's cycling, then the evaluation is that the machine properly taught itself. And then if it said, for example, it was running, then the evaluation is the machine is wrong. And then we can improve. So for example, in this case, there wasn't really much to improve, but if I had another use case where it got wrong and the evaluation was that the model is failing, then I would improve it and maybe let it run for a couple more hours, etc. So how machines have traditionally worked is we give an input and we give a process, and then the machine gives us an output, right? So for example, I give the input 3 and the process is +2, it outputs 5. 50 plus 2, 52, 709 plus 2, 711. So we predefine what is the input and what is the process, and we let the machine calculate the output. But instead of that, what we can do in machine learning is that we can give it the input and the output and let the machine calculate the process, right? So in this case, what I do is I gave the machine 3 and 5, I gave it 50 and 52, and then I gave it 709 and 711. And the machine, using this data set, calculated the possible combinations and then told me that the process is +2. So this is the difference between traditional approach and machine learning approach, where instead of, for example, in the cycling case, instead of giving the machine, this is how you identify a cycle, this is the image, and then outputting whether it is a cycle, I tell the machine, this is the image, this is the cycling. I want you to identify how it's cycling, right? So basically, it can be used. Machine learning is used for two major things. One is to classify data, such as the image recognition example, right? So whether it's cycling, whether it's running, whether it's, for example, dancing. So we can give the image and then it classifies whether it's one of those 6 categories. And then otherwise, it can also make predictions. So in the Timmy case, one second. In the Timmy case, yeah, over here, we basically made predictions as to whether Timmy will like it or he won't like it. So these are basically the two main essential use cases of machine learning. So for example, one of the use cases that I've used as well, and a lot of scientists are using these days, is identifying impulses. So they tell they give the machine the impulse code, for example, GCA, blah, blah, blah. And then they tell the machine, this was the impulse code for raising the hand. And then after millions of data sets, the machine can automatically recognize what is raising the hand, what is raising the foot, instead of manually typing a lot and a lot and a lot of code to teach the machine. So that is how machine learning essentially works. So what's the difference between traditional machines and machine learning? Traditional machines use huge data sets occupying vast amounts of space. They're extremely slow and lengthy, and each logic has to be handwritten with perfection. One small error, and the machine cannot identify anything, right? But in the machine learning, we can use a much smaller data set. Like, for example, in the Timmy's example, only 20 data sets, 20 toys, basically. And then the computer observes and analyzes each single data set. And then based on that, based on those 20 toys, the machine will predict what toy Timmy likes and what toy Timmy doesn't like. And the best part is you do not even have to make the simple algorithms. They're pre-programmed. All you have to do is import them and use them. So there are these big mathematicians and physicists that make these programs beforehand for you to use. You don't have to port them all yourself from scratch, right? So a lot of you are probably confused. What's the difference between machine learning and artificial intelligence then? So the artificial intelligence is basically the ability of a program or code to make decisions on its own without the help of humans. However, this does not necessarily means decision through machine learning. So for example, when we saw the long code, where, for example, the machine was determining what is cycling, what is not cycling, that technically was artificial intelligence. The machine was making decisions. It just wasn't using machine learning. It was using traditional learning approach, and it was making decisions, but it was still decisions. So it's still artificial intelligence. But machine learning is one of the ways in which an AI can make a decision through properly learning and executing instructions, as well as learning for itself. So now you don't have to teach the AI, it can teach itself. All you have to do is give it a little data set, which you can get from anywhere, and then the AI will teach itself. So there's 3 levels to this. So artificial intelligence is any technique that lets computers mimic human intelligence, like we just discussed. Machine learning is a subset of AI. And one of the methods artificial intelligence can use in order to make decisions. There are a lot of other ways artificial intelligence can make decisions, for example, using if statements, etc. And then what we just went through, where we gave data set and the machine teaches itself, that is called deep learning. So 1 second, let me just zoom out. So over here, artificial neural networks, well, that's what we use in deep learning. So this method of machine learning, obviously there's other methods, but this method of machine learning is called deep learning, where the machine essentially creates little nodes. Okay, I won't dive into nodes and all that, but essentially the machine creates an algorithm for itself to use. That is called deep learning based on data sets. But we can also have evolutionary machine learning, right? So that is the second most common type of machine learning, and it is mostly essentially used in games. So do you know, basically it's basically a mimic of human evolution. So I hope you know what human evolution is. It's basically humans evolved to become better and better and better. The same way, the machine learning AI can evolve over time to become better and better. So for example, I had this game, right? I had this very simple game where if the character moves right, they gain a point. And if the character moves left, they lose a point. And if they reach the trophy, whatever time there is, that is how long it took them to win the game. So in this game, the objective is to move right and collect the trophy as fast as you can. So I want to show you this game called Flappy Bird. And this is really important to the discussion we're going to proceed with, because Flappy Bird is a very simple game, which we can easily program. Implement machine learning to. So I want you to look at this. So as you can see, there's two pipes there. 1 second, let me pause it. So 1 sec. I'll pause it right here. Yeah, so as you can see, there's two pipes there. And based on the distance from the pipes, the machine can decide whether it should jump or whether it shouldn't jump, right? So the idea is to dodge the pipes. And if you hit the pipes, the game is over. It's a very simple game. So how do we decide when to jump? Well, you give the machine inputs, which are called nodes. This can be distance from top pipe, distance from lower pipe, and distance from ground, right? And what it does is we give it modifiers. So modifiers are values that determine how important a node is, essentially. So for example, distance from top pipe, that may not be the most important input, because maybe we'll dodge it anyways because of gravity or other things. So basically, modifiers tell you how important a node is in making decisions. So then what we do is we multiply the input with the modifier, and then we add them up to find out a decision value. So for example, I had 30 from the top pipe. It would get multiplied by 1.51. Same with this, same with this. We add all of those values up, and then we get one value called a decision value. This will always be numerical. You won't have any other thing like words or anything like that, right? So essentially, there's only three inputs you need to give: distance from top pipe, distance from lower pipe, and distance from ground. You multiply those values with a modifier. So if there's a large modifier, like in this case, 11.29, that means that value is very important because it's being enlarged. And then, for example, distance from lower pipe, that's 1.35, so it's not that important. We add them up, we get a decision value. And then we can use this decision value to determine what we do. So for example, if decision value is less than 50, then we jump, otherwise we don't jump. So essentially, we just use one if statement to check whether that decision value tells us to jump or not jump. But the trick here is to identify what should be the modifiers, because there's so many you could have 1 to infinity. So how do you know which value is important and how important it is? So that is where evolutionary learning kicks in. So unlike deep learning, evolutionary learning actually uses only numerical values and does not have any graphs or anything of that sort. So in the case of evolutionary in machine learning, what we can do is take, for example, this game. So this is a game I coded on my own. I mimicked the game. But what I did was first we make 100 birds with random modifiers. We don't know what the modifiers are. They're going to be 100 random modifiers. And this 100 birds are called a population, right? Just like humans. So human population, just like that, we have 100 birds, which are called a population. Then as the game progresses, one bird will slowly die, each bird, I mean, until 0 birds are remaining, right? So until all birds die, we let the game run. Then whichever 5 birds get the best scores, their modifiers are chosen. So for example, one bird who made it the furthest had a modifier of 20, 21, and 22. So we know that those modifiers are good modifiers. That's why the bird made it the furthest, right? And the bad modifiers are the ones that immediately died from the start. So we take the good modifiers, and then the next 100 birds, which will be the next population, we'll give that modifier and surrounding values to those 100 birds. Then we'll run it again. For example, we got 20.5, 20.1, and 20.6. We take those modifiers, and then we know those are good modifiers, and we rerun it over and over and over until we get the perfect set of modifiers. So I can actually show you this through a video. I think that will be pretty easy to understand. So in this case, as you can see, there's 100 birds, 20 birds, and they immediately start to die, right? But as soon as we get to like generation 3, there's already an improvement. And it died. And over the course, it's just constantly teaching each generation how to be better than the last generation. So I'll let this play. So with 8 generations in, we've got one bird that's performing well. Okay, I guess not. But it's constantly teaching itself how to be better and better and better. There may be some generations which did worse than the last ones, but that's just one of cases. So then, as you can see, generation 16 did better than any previous generation. I'll skip this forward just to show you the end. So yeah, by generation 20, or I guess not 20. Yeah, so by generation 21, the birds essentially taught themselves through continuous process which modifiers are the best modifiers, because whichever birds make it the furthest, those modifiers are good. And then we use those to kind of reproduce the younger generations. So I'll give you the advantages and disadvantages of machine learning. So advantages: efficiency data managing, continuous improvement, lots of applications, trend identification, and pattern identification. And then, okay, I'll just explain. So efficient data managing, that's basically now you don't need like 20 people managing which data goes where. You can just have one machine that's pre-trained, that is already trained essentially, which can manage your data for you. Continuous improvement is in the sense that, like I just showed you, every generation keeps getting better and better and better. So there's constantly an improving stage without me having to do anything. The machine is teaching itself. Obviously, huge applications. Machine learning is everywhere. You can go finance, engineering, medical. Machine learning is essentially everywhere. Trend identification. So for example, you had the stock market or property rates or anything, or exchange rates. So anything of that sort. Machine learning models are essentially very, very good at identifying trends and predicting where the price will go based on data. And then pattern identification. So this is something that's not used a lot, except in works like art or anything like that, where machines can identify patterns that humans really like, and then put those patterns in their own drawing. And then disadvantages: data acquisition, time and space, time consuming, high error possibility, and algorithm selection. So data acquisition, what is that? So basically data acquisition is, for example, Timmy, I had 20 toys in that case. That is my data. I already have those toys. But data acquisition means I have to continuously go to Timmy and ask, do you like this toy? Do you like this toy? Do you like this toy? 20 times. So that is called data acquisition. And in this case, it's a very, very simple example, only 20 times. But think about when you have like 1 million toys or 1 million, for example, subcategories for stock exchange, you would have to get a lot of data, and you sometimes have to figure out how to get that data. Time and space. So needless to say, when you're bringing in so much data, it requires a lot of memory and a lot of time to process. Your machine won't just snap your fingers and it learns, because machine learning takes a large amount of time. Even for a simple Flappy Bird game, I think it took 21 generations. So, and it only has 3 inputs. So imagine 1,000 inputs. It's going to take a huge amount of time, right? High error possibilities. There are cases where you may get errors, although these are very, very little. So you're not going to get errors too often. But there are times when the machine just teaches itself the wrong thing. Like recently, I remember Twitter made a machine learning program that learns from tweets and then makes its own tweets, right? But what happened was it learned from all the bad hate tweets and then started tweeting out very, very wrong stuff, essentially very offensive stuff. So that is kind of error possibilities that you cannot control. You kind of have to let the machine learn on itself. And if it learns wrong, you have to stop it. And then algorithm selection. So because, like I said, mathematicians pre-program these algorithms, there's so many algorithms. There's linear regressors, natural regressors, a lot of them. So you have to kind of pick the right algorithm to use. Now, this is not nearly as hard as programming your own algorithm. That's very bad and takes a lot of time. So, but still, selecting your algorithm can be sometimes a hurdle. But make no mistake, advantages overweigh the disadvantages by a good amount. It's only the initial investment that you have to spend to decide your algorithm. Otherwise, the advantages are huge. So there's multiple opportunities of machine learning, of course. So there's image recognition, like the emoji one I just showed you, voice recognition, optical recognition, customization, data analysis, and memory data. Now, I won't go through these. You feel free to Google them at your own time. But I essentially wanted to get the idea across that there are huge opportunities in machine learning, right? So, oh yeah, that is it. Thank you.